Chapter 4: Cryptography. One of Ethereum's foundational technologies is cryptography, which is a branch of mathematics used extensively in computer security. Cryptography means secret writing in Greek, but the study of cryptography encompasses more than just secret writing, which is referred to as encryption. Cryptography can, for example, also be used to prove knowledge of a secret without revealing the secrets, for example with a digital signature, or to prove the authenticity of data, for example with digital fingerprints, also known as hashes. These types of cryptographic proofs are mathematical tools critical to the operation of the Ethereum platform, and indeed all blockchain systems, and are also extensively used in Ethereum applications. Note that at the time of publication, no part of the Ethereum protocol involves encryption. That is to say, all communication with the Ethereum platform and between nodes, including transaction data, are unencrypted and can be read by anyone. This is so everyone can verify the correctness of state updates and consensus can be reached. In the future, advanced cryptographic tools such as zero-knowledge proofs and homomorphic encryption will be available that will allow for some encrypted calculations to be recorded on the blockchain while still enabling consensus. However, while provision has been made for them, they have yet to be deployed. In this chapter, we will introduce some of the cryptography used in Ethereum, namely public key cryptography, PKC, which is used to control ownership of funds in the form of private keys and addresses. Keys and addresses. As we saw earlier in the book, Ethereum has two different types of accounts: externally owned accounts, EOAs, and contracts. Ownership of Ether by EOAs is established through digital private keys, Ethereum addresses, and digital signatures. The private keys are at the heart of all user interaction with Ethereum. In fact, account addresses are derived directly from private keys. A private key uniquely determines a single Ethereum address, also known as an account. Private keys are not used directly in the Ethereum system in any way. They are never transmitted or stored on Ethereum. That is to say that private keys should remain private and never appear in messages passed to the network, nor should they be stored on-chain. Only account addresses and digital signatures are ever transmitted and stored on the Ethereum system. For more information on how to keep private keys safe and secure, see the Control Responsibility section. Access and control of funds is achieved with digital signatures, which are also created using the private key. Ethereum transactions require a valid digital signature to be included in the blockchain. Anyone with a copy of a private key has control of the corresponding account and any Ether it holds. Assuming a user keeps their private key safe, the digital signatures in Ethereum transactions prove the true owner of the funds because they prove ownership of the private key. In public key cryptography-based systems, such as that used by Ethereum, keys come in pairs consisting of a private key and a public key. Think of the public key as similar to a bank account number, and the private key as similar to the secret PIN. It is the latter that provides control over the account, and the former that identifies it to others. The private keys themselves are rarely seen by Ethereum users. For the most part, they are stored in encrypted form in special files and managed by Ethereum wallet software. In the payment portion of an Ethereum transaction, the intended recipient is represented by an Ethereum address, which is used in the same way as the beneficiary account's details of a bank transfer. As we will see in more detail shortly, an Ethereum address for an EOA is generated from the public key portion of a key pair. However, not all Ethereum addresses represent public-private key pairs. They can also represent contracts, which, as we will see in the Smart Contracts chapter, are not backed by private keys. In the rest of this chapter, we will first explore basic cryptography in a bit more detail, and explain the mathematics used in Ethereum. Then we will look at how keys are generated, stored, and managed. Finally, we will review the various encoding formats used to represent private keys, public keys, and addresses. Public key cryptography and cryptocurrency. Public key cryptography, also called asymmetric cryptography, is a core part of modern-day information security. The key exchange protocol, first published in the 1970s by Martin Hellman, Whitfield Diffie, and Ralph Merkle, was a monumental breakthrough that incited the first big wave of public interest in the field of cryptography. Before the 1970s, strong cryptographic knowledge was kept secret by governments. Public key cryptography uses unique keys to secure information. These keys are based on mathematical functions that have a special property. It is easy to calculate them, but hard to calculate their inverse. Based on these functions, cryptography enables the creation of digital secrets and unforgeable digital signatures, which are secured by the laws of mathematics. For example, multiplying two large prime numbers together is trivial, but given the product of two large primes, it is very difficult to find the prime factors, a problem called prime factorization. Let's say we present the number 8018009 and tell you it is the product of two primes. Finding those two primes is much harder for you than it was for me to multiply them to produce 8018009. Some of these mathematical functions can be inverted easily if you know some secret information. In the preceding example, if I tell you that one of the prime factors is 2003, you can trivially find the other one with a simple division. 8018009 divided by 2003 equals 4003. Such functions are often called trapdoor functions because they are very difficult to invert, unless you are given a piece of secret information that can be used as a shortcut to reverse the function. A more advanced category of mathematical functions that is useful in cryptography is based on arithmetic operations on an elliptic curve. In elliptic curve arithmetic, multiplication modulo a prime is simple, but division, the inverse, is practically impossible. This is called the discrete logarithm problem, and there are currently no known trapdoors. Elliptic curve cryptography is used extensively in modern computer systems, and is the basis of Ethereum's use of private keys and digital signatures. Note: take a look at the following resources if you're interested in reading more about cryptography and the mathematical functions that are used in modern cryptography. 1. Cryptography. 2. Trapdoor function. 3. Prime factorization. 4. Discrete logarithm. 5. Elliptic curve cryptography. In Ethereum, we use public key cryptography, also known as asymmetric cryptography, to create the public-private key pair we have been talking about in this chapter. They are considered a pair because the public key is derived from the private key. Together, they represent an Ethereum account by providing, respectively, a publicly accessible account handle, the address, and private control over access to any Ether in the account and over any authentication the account needs when using smart contracts. The private key controls access by being the unique piece of information needed to create digital signatures, which are required to sign transactions to spend any funds in the accounts. Digital signatures are also used to authenticate owners or users of contracts, as we will see in the smart contracts chapter. Tip: in most wallet implementations, the private and public keys are stored together as a key pair for convenience. However, the public key can be trivially calculated from the private key, so storing only the private key is also possible. A digital signature can be created to sign any message. For Ethereum transactions, the details of the transaction itself are used as the message. The mathematics of cryptography, in this case, elliptic curve cryptography, provides a way for the message, i.e. the transaction details, to be combined with the private key to create a code that can only be produced with knowledge of the private key. That code is called a digital signature. Note that an Ethereum transaction is basically a request to access a particular account with a particular Ethereum address. When a transaction is sent to the Ethereum network in order to move funds or interact with smart contracts, It needs to be sent with a digital signature created with a private key corresponding to the Ethereum address in question. Elliptic curve mathematics means that anyone can verify that a transaction is valid by checking that the digital signature matches the transaction details and the Ethereum address to which access is being requested. The verification doesn't involve the private key at all. That remains private. However, the verification process determines beyond doubt that the transaction could have only come from someone with the private key that corresponds to the public key behind the Ethereum address. This is the magic of public key cryptography. Tip: there is no encryption as part of the Ethereum protocol. All messages that are sent as part of the operation of the Ethereum network can be read by everyone. As such, private keys are only used to create digital signatures for transaction authentication. Private keys. A private key is simply a number picked at random. Ownership and control of the private key is the root of user control over all funds associated with the corresponding Ethereum address, as well as access to contracts that authorize that address. The private key is used to create signatures required to spend Ether by proving ownership of funds used in a transaction. The private key must remain secret at all times, because revealing it to third parties is equivalent to giving them control over the Ether and contracts secured by that private key. The private key must also be backed up and protected from accidental loss. If it's lost, it cannot be recovered and the funds secured by it are lost forever too. Tip: the Ethereum private key is just a number. One way to pick your private keys randomly is to simply use a coin, pencil, and paper. Toss a coin 256 times and you have the binary digits of a random private key you can use in an Ethereum wallet. The public key and address can then be generated from the private key. Generating a private key from a random number. The first and most important step in generating keys is to find a secure source of entropy or randomness. Creating an Ethereum private key essentially involves picking a number between 1 and 2 to the 256th power. The exact method you use to pick that number does not matter as long as it is not predictable or deterministic. Ethereum software uses the underlying operating system's random number generator to produce 256 random bits. Usually, the OS random number generator is initialized by a human source of randomness, which is why you may be asked to wiggle your mouse around for a few seconds or press random keys on your keyboard. An alternative could be cosmic radiation noise on the computer's microphone channel. More precisely, a private key can be any non-zero number up to a very large number, slightly less than 2 to the 256th power. A huge 78-digit number, roughly 1.158 times 10 to the 77th power. The exact number shares the first 38 digits with 2 to the 256 and is defined as the order of the elliptic curve used in Ethereum. To create a private key, we randomly pick a 256-bit number and check that it is within the valid range. In programming terms, this is usually achieved by feeding an even larger string of random bits collected from a cryptographically secure source of randomness into a 256-bit hash algorithm such as KCAC256 or SHA-256, both of which will conveniently produce a 256-bit number. If the result is within the valid range, we have a suitable private key. Otherwise, we simply try again with another random number. Tip: 2 to the 256, the size of Ethereum's private key space, is an unfathomably large number. It is approximately 10 to the 77th in decimal. That is a number with 77 digits. For comparison, the visible universe is estimated to contain 10 to the 80th atoms. Thus, there are almost enough private keys to give every atom in the universe an Ethereum account. If you pick a private key randomly, there is no conceivable way anyone will ever guess it or pick it themselves. Note that the private key generation process is an offline one. It does not require any communication with the Ethereum network, or indeed any communication with anyone at all. As such, in order to pick a number that no one else will ever pick, it needs to be truly random. If you choose the number yourself, the chance that someone else will try it is too high. Using a bad random number generator is even worse, because it is even more obvious and even easier to replicate. Just like with passwords for online accounts, the private key needs to be unguessable. Fortunately, you never need to remember your private key, so you can take the best approach for picking it, namely true randomness. Warning! Do not write your own code to create a random number or use a simple random number generator offered by your programming language. It is vital that you use a cryptographically secure pseudo-random number generator, such as CSPRNG, with a seed from a source of sufficient entropy. Study the documentation of the random number generator library you choose to make sure it is cryptographically secure. Correct implementation of the CSPRNG library is critical to the security of the keys. The following is a randomly generated private key shown in hexadecimal format: F8F8A2 315.